This video we're going to talk about the Arrhenius equation. And from the previous two videos, we know that there are two requirements for products. Number one, the collision energy must be greater than the energy of activation. And the second thing is we must have proper orientation. So Arrhenius proposed the following equation. K is equal to A times e to the minus EA divided by RT, where A is a constant, or sometimes referred to as a frequency factor. So this takes into account the orientation, and we have activation energy and temperature also in this particular relationship. If we can rearrange this a little bit to kind of get a more convenient form, we can take the natural log of both sides. So that's going to be the natural log of K is equal to the natural log of A e to the minus EA divided by RT. And this will help us rearrange this into more of a point form, and we'll arrange it into y equals mx plus b. So when we take an ln of something with an exponential expression, we can then take the EA divided by R, or the minus EA divided by R, bring it outside of this particular expression. That's going to be times 1 over the temperature plus the natural log of A. So here is our particular expression, and we can put this in y equals mx plus b form. Okay? Our y variable is going to be the natural log of K, so we're going to plot that on the y-axis. Our x variable is going to be 1 over the temperature. The slope is going to be equal to negative EA divided by R. And our y-intercept then is going to be the ln of A, which is typically a constant. So if we would show a plot of this, and we would graph the natural log of K on the y-axis and 1 over the temperature on the x-axis, which is what Arrhenius did, he got a linear plot that looks something like this. And the slope is going to be equal to negative EA divided by R. Okay? And this is very similar to what we saw in previous chapters with the Clausius-Clapeyron equation. All right? So this can be kind of confusing, but typically when we look at equations like this, we want two data points. So one data point, there are two data points along this line right here. Okay, so if we have two data points, we can put this in a more point-like form, right? So if we have two data points, so data point number 1, we'll say is going to be the ln of K1. That's going to equal negative EA divided by R times 1 over T1 plus the ln of A. And data point number 2 is going to be the ln of K2, which will equal negative EA divided by R times 1 over T2 plus the ln of A. If we rearrange these two and we kind of set the natural log of A, which is a constant, equal to each other, we can get the following expression. We'll have ln of K2 minus ln of K1 is going to equal negative EA divided by R times 1 over T1 minus 1 over T2. We can further manipulate this expression to give what it shows in our textbook to be the ln of K2 divided by K1. Remember, when we have two expressions inside a parenthesis in a natural log, that's like subtracting them. Okay, that's going to equal EA divided by R times 1 over T1 minus 1 over T2. And I noticed I had a mistake here when I initially put this expression in. T2 should be this, and this guy right here should be T1. So This will map up with what we have in our textbook, and this formula right here is the two-point form of the Arrhenius equation, where our ln of K2 over K1 is going to equal the energy of activation divided by R times the quantity 1 over T1 minus 1 over T2. And this equation right here is going to be very, very important to solving problems involving the Arrhenius equation, collisions, and orientation. So we will look at an example problem of this in the next video.